NMR is an important topic in organic chemistry and also in MCAT, and to know the fundamentals of proton and carbon-13 is going to be very useful in your MCAT problem solving. So we will talk about proton NMR in this short video. I won't give you a lot of theory or background. I'll just give you the fundamentals that you need to know so that you can solve a spectroscopy problem. So if you look at NMR spectroscopy, it typically varies. The x-axis is going to be anywhere from 0 ppm all the way to 12 ppm, and the hydrogen in a molecule is visible in an NMR spectroscopy, or for an NMR spectrophotometer, which is going to give out signals in the form of an NMR spectrum. Okay, so anytime you have a hydrogen, the hydrogen can be attached to a carbon or an oxygen or a nitrogen or anything else. All those hydrogens in a molecule are going to be visible. Now, depending on how much electron density there is, okay, the hydrogen is going to appear at different regions in the NMR, proton NMR spectrum. Generally speaking, not always, there are a couple of other things that happens also, but generally speaking, more electron rich a hydrogen is, the lower ppm value it is going to appear in. That's the first simple rule you need to know. So if you take, for example, methane, okay, this hydrogen in methane appears at somewhere around 0.5 ppm. ppm is the I don't say a unit, but it is the notation it is used to represent numbers in the NMR x-axis scale. So this hydrogen has a certain electron density around it, and therefore it is going to appear at 0.5 ppm. Now if you remove one of the hydrogens from methane and put chlorine in instead, you get chloromethane. And chloromethane, the hydrogens here are now going to have a lower electron density because the chlorine pulls electrons from carbon due to different higher electronegativity, and that in turn is going to pull electrons away from the hydrogens. Therefore the hydrogen electron density is now depleted compared to methane, and for that reason you can expect, or you can actually see these hydrogens to appear around 3.0 ppm. I'm just giving you whole numbers, but the number is approximately correct, and also it is going to emphasize an important point. Okay, now if you if you take one of the hydrogens off again and replace that with another chlorine, you get dichloromethane, which means two chlorine atoms are going to withdraw electrons from the carbon, which in turn is going to take more electrons away from the hydrogen, and that will reduce the electron density on this hydrogen even further, and therefore these two hydrogens are going to appear at 5.0 ppm in a proton NMR. Now guess what happens when you convert the other hydrogen also into a chlorine in the molecule, and look at the NMR spectrum. Okay, so now this hydrogen is going to appear at 7.0 ppm. So this is an important concept that you need to know. The more electron that is taken away from the hydrogen, the higher ppm value it is going to appear in. So this is purely based on inductive effect. Okay, that is one of the main reasons or one of the main factors that controls where the protons appear in an NMR spectrum. Now there is one more factor, which is what is called as an internal effect, a ring current effect. So that is something that we can talk shortly. So first let me explain what's going on here. If you take, say for example, propane, the terminal hydrogens are going to appear at a lower ppm value compared to the hydrogens here in the middle, because this carbon is connected to three hydrogens and only one other carbon. Remember, carbon's electronegativity is 2.1. okay, so this carbon is going to have three hydrogens and one carbon, whereas this carbon is going to have two other carbons attached to it. That means this carbon is going to have slightly lower electron density. Therefore the connected hydrogens are going to appear at a higher ppm value because they will have slightly lower electron density compared to the hydrogen on the terminal carbon. Therefore primary carbons, you can expect them to appear around 0.8 ppm, but you can say 1 ppm to be approximate, whereas the hydrogens here, they are going to be around 1.2 1.3 ppm for that reason. Now guess what happens when you have a tertiary carbon and hydrogens connected to that. So for example, if we have tertiary butane and the hydrogen here, this hydrogen is going to appear at an even higher ppm value, like 1.5 1.5 or 1.6, slightly more electron deficient than the other two, and therefore it is going to appear a little higher ppm value. So between the three, you should be able to now distinguish between primary, secondary and tertiary by looking at a proton NMR spectrum. That's one. Now the next thing that appears in an NMR spectrum that is a little bit more downfield or a higher ppm value is when you have hydrogens that are attached to an aromatic ring. So when you look at the carbon hydrogen here that is next to an aromatic ring, which is what you call the benzylic hydrogen. This is the benzylic carbon, this is the benzylic hydrogen. The benzylic hydrogen appears around 2.1, 2.2, a little bit more downfield or a higher ppm value compared to what you see for typical alkanes. Okay, so that's that. And you can ignore something like CH2, nitrogen, CH2, sulfur. You can ignore these things. Now other important proton signal in an NMR is something that is attached to a carbonyl. So if we have, say for example, a ketone, so these hydrogens are going to appear around 1.0, okay, because it's a terminal hydrogen, right, somewhere between 0.5 and 1.0, whereas these hydrogens are going to be a little bit more downfield or a higher ppm value. I can expect that to come somewhere around 1.5, all right, whereas these hydrogens are going to be significantly electron deficient because you have the carbonyl taking electrons away from the carbon attached to it. Therefore these hydrogens are going to be at an unusually higher ppm value, which is 2.1 ppm. So this one, say 1.0, this is say 1.2, 1.3, and this one is going to be 2.1. okay, so 2.1 to 2.5 you can expect aromatic CH2s, which is the benzylic hydrogen, and also hydrogens attached to a C double bond O. Okay, alright, so that's the next thing that you need to know. Now the next set of hydrogens that will come at a higher ppm value is the hydrogens connected to an oxygen. It's like, say for example, you have an ether, right? So these hydrogens will be at 1.0 because it is a terminal hydrogen which is attached to a carbon that is attached to only one other carbon. So 1.0 is what I would expect, right? Whereas these hydrogens, they are going to be at a much higher value because this oxygen has a very high electronegativity, which takes electrons away from that that carbon here, which in turn is going to take electrons away from that hydrogen. Okay, so this I can expect to be around 4.0, like 3.8 to 4.0. And notice they are all going to be ranges. All right, there's a kind of a slightly wide range. So but like you can typically expect these hydrogens, that is alpha to an oxygen, to be at a 4.0 range. Okay, and remember when we looked at the chloromethane, right, when you have CH3 attached to a chlorine has very similar electronegativity to oxygen, and you can expect the hydrogen that is attached to a chlorine to be around 3.0, right? So an oxygen also it's somewhere going to be between 3 and 4 for a hydrogen that is attached to an oxygen. Okay, so that's the next thing. So until now we have only been seeing inductive effects, all right, that is affecting where a proton is going to appear in a proton NMR. If you look at alkenes, right, if you look at alkene, like say for example cyclohexene, so in cyclohexene these hydrogens, right, which is attached to an sp2 carbon, okay, they are attached to a carbon whose electronegativity is 2.5, right, 2.5 for carbon, 2.1 for hydrogen, which is very similar to what you would expect for a typical alkane. So the alkane, all these peaks are going to be less than 1.5. None of the peaks are going to be above 1.5, right, generally speaking. Whereas when you have an alkene bond, what happens is there is an internal current in the molecule that is generated from the pi bond, and that deshields the hydrogen and makes the hydrogen sense the NMR field more strongly than a typical sp3 carbon, right? So the pi bond creates a internal current, therefore that deshields the hydrogen, due to which the alkene bonds appear between 5 and 6. Even though you see it going from 4.5 to 7, generally it is going to be between 5 and 6, or maybe we can even say 4.5 to 6. All right, so that is not due to inductive effect, but it is due to the internal current in the molecule. All right, so alkenes have that. Okay, and this is a pretty distinct region. Like now you can see that only alkenes are present here. Here it's a little crowded and cluttered, right? Whereas here you can see that when you have an alkene proton, that it is going to be somewhere between 4.5 to 6 ppm, and that's for the reason. And when you look at something like a benzene ring, which again has double bonds in the molecule, and you might wonder why aren't these hydrogens appearing in the same region as an alkene which appears between 4.5 and 6. Why does this aromatic hydrogen appear at such a high ppm value? That's because in addition to that ring current, like in addition to the pi current I was talking about, there is also a ring current that happens in the molecule, right, which de-shields the hydrogens even further. So because the hydrogen is very de-shielded, it is going to sense a very strong electromagnetic field, and for that reason it is going to appear at a higher ppm value. Okay, so until now that's basically what you need to know. And if you look at an aldehyde, you should realize that an aldehyde is very much like a carbon with an alkene double bond, but except it not only has the internal current, it also has an oxygen that is going to withdraw electrons through an inductive effect, making this hydrogen very highly electron deficient as well as de-shielded because of the internal current. That makes this aldehyde bond, sorry, the hydrogen in the aldehyde functional group appear at 9 to 10 ppm. Okay, so aldehydes are one of the most distinctly recognizable peaks in a proton NMR spectrum. Okay, and finally you have carboxylic acid. If you look at a carboxylic acid, you know that the oxygens are going to take electrons away from the hydrogen very easily, right, leaving this as H+. So even when it is bound, the hydrogen is very highly electron deficient, making it appear at an extremely high ppm value, or what we call the downfield region in the NMR spectrum. And here I skipped OH and NH, and you can remember, I mean you can kind of understand what's going on here. If an oxygen connected to a carbon and its hydrogen is going to appear at a 4 ppm, then a hydrogen directly attached to an oxygen is going to appear at a much higher ppm value. And it's a very broad range, and the reason it's a broad range is because alcohols can hydrogen bond, right, and the hydrogens are very easily exchangeable. Therefore there's a huge range in bond lengths this the OH bond or the NH bond can have because of hydrogen bonding. So since there's a huge range or variability in the bond characteristics, the ppm values in which they appear also is going to be quite broad. Okay, so there are going to be some really short bonds, and there are going to be some really long bonds, and there are going to be some oxygens that have a higher electron density which is going to have a bond with hydrogen. For all those reasons it's very broad, but generally you can expect it to be somewhere between 2 and 4. Just to give you an idea, if you take water and you run the NMR spectrum of pure water, you can expect the peaks to be around 4.5, 4.8 ppm. So hopefully this gives some idea of what to look for in an NMR spectrum, proton NMR, and the reason behind why the peaks appear where they appear.